In this section, we're looking at the applications of double integrals. So we've already done one application, which is computing volumes. We're also going to do area of surfaces in the next section, but in this one, it's more the physical applications like computing mass, electric charge, center of mass, the moment of inertia. This section also goes into probability, which is calculus-based, which is a lot of fun, but since y'all lean towards engineering, we're going to focus on the engineering ones. In section 8.3, in chapter 8, we definitely did arc length and surface area using integrals, but we didn't necessarily do the center of mass or the other ones. The probability can be done there as well. What we're looking at here is we're going to look at this region D, and with a double integral, we can consider a lamina with variable density. Now, the word I'm saying is lamina, and it means a thin plate. So when they talk about a lamina, they're talking about a very thin plate, and we're going to look at the density of this. So we're going to look at the region D, which is the nice pretty shaded area here of the xy plane, and the density at this specific point xy is given by a function, and it's rho. This is kind of a cursive-y looking p, so it's rho of xy, and rho is a continuous function on D. And then we can find that the mass of the lamina, because we're going to do the double integral. There's a lot of math that goes into this, a lot of explanation, but the double integral over the region D of rho of xy with respect to the area. Good news, you don't have to memorize these formulas. I will give you a reference sheet for them, and you can use them when you take your test that covers this section. So this is your formula for mass. And then physicists also consider other types of density in the same manner. For example, if an electric charge is distributed over region D, so imagine that over this region D we have an electric charge, and the charge density is given by, it's a little sigma. So the little sigma here of xy, capital sigma is summation, little sigma is this cursive-y looking O. Then the total electric charge Q is given by the double integral over D of sigma of xy with respect to the area. So this is the electric charge Q. Aren't you glad I'm not going to make you memorize these? And up above, let's go ahead and go back and label those. This would be our, the second one here. This is our mass, and this is our continuous function in the region D that will help us find the mass. Remember, it's the Greek letter rho, and it'll help us find our mass. So let's do an example or two. In this problem, charge is distributed over the triangular region D in the figure below, so that the charge density at xy is sigma of xy equals xy, measured in coulombs per square meter, which is c per meter squared, and find the total charge. So if you remember, when we talked about the formulas in the previous screen, in order to find an electrical charge, we say that Q is equal to the double integral over the region of sigma of xy with respect to the area. So we're going to use our double integral in order to figure the electric charge. We're given a rho, so we're going to say Q equals the double integral. I'm going to leave some spaces here. And our sigma is xy. And then we need to determine dA. Now this is the type where we're going to go from 1 minus x to 1 for the y value. So I'm going to put 1 minus x to 1 with respect to y. And then my x goes from 0 to 1. So 0 to 1 with respect to x. Because there's an x in my bounds, then I'm going to integrate first with respect to y. So now we're going to do this integral here. So we're going to say the integral from 0 to 1. When we integrate this with respect to y, we get 1/2 y squared. We're going to keep the x here. 1/2 y squared with x from 1 minus x to 1. And then we have with respect to x. So we're going to say the integral from 0 to 1. So we have 1/2 x times 1 squared is 1 minus 1 minus x squared with respect to x. Now consider 1 minus x squared. Remember that you have to write it twice and do FOIL. A lot of students mix that up and don't do it, so be careful with that. So I have 1 minus 2x plus x squared with respect to x. So I have 1/2 times x, and 1 minus 1 is 0. So we have 2x minus x squared distributing that negative with respect to x. Now we're going to distribute the x. I'm going to pull the 1/2 out front. So we have 2x squared minus x to the third with respect to x. So now we can integrate, and 2x squared becomes 2/3 x to the third minus 1/4 x to the fourth from 0 to 1. So when we put in ones, we have 2/3 minus 1/4. That's terrible. So we have 2/3, it just looks badly, minus 1/4, minus 0, minus 0. I need common denominators, and I'm not going to do them in my head, so if I do, I will definitely make a mistake. We could leave off the minus 0, it's not important. So 4 times 2 is 8, and 3 times 1 is 3. So we have 1/2 times 5 over 12, which gives us 5 over 24. When we do 5 over 24, the total charge is 5 over 24 columns. So we just put the C here. The density is measured in columns per square meter, but the charge is just in columns because we're not talking about the region anymore. And I hope that makes sense. So when we look at moments and centers of mass, the moments are going to get us to the centers of mass, and all of this you can pause and read through it, but it tells us that if you look at this, to find the center of a mass of lamina, the problem is we're looking at something with a variable density. Like if you were looking at something with a constant density of like a set number, it's not as difficult to deal with, but the calculus comes into play because we have such a variable density, and it's not linear. It's a nice, pretty curve often. So if you look at the fact, it says up here, recall from chapter 8, up in here, recall from chapter 8, we define the moment of a particle about an axis as the product of its mass and the distance from the axis. So here they defined a moment of the entire lamina about the x-axis and a moment of the entire lamina about the y-axis. Now when we get here, the center of mass, this is what's important, is these two formulas. So we're going to pull this into the center of mass formulas, but this is where it comes from. The moment, you notice that it looks very similar to your density formula, the mass formula that we had. And here's what's important here. If you think about the center of mass, it says the physical, this last part down here, the physical significance is that the lamina behaves as if the entire mass is concentrated at the center of mass. So the lamina balances horizontally when supported at the center of mass. So if you think about the center of mass, that's where your balancing point could be. So again, here are pretty formulas that I'm not going to make you memorize. I'm going to give them to you on a reference paper. And so that says the coordinates of the center of mass of the lamina occupying the region D and having the density function stated here below are these. So what we're finding here really is the point for the center of the mass. So this is the x value point right here, and this is the y value point right here. And this is the moment formula we talked about in the previous screen over the mass. So this part right here is the moment formula, and you put it over the mass. That's important because what we're going to do is we're going to scratch all of that, and we're going to say that we're going to find the x and the y values from these points. So here's the x value for a center of mass, and here's the y value for a center of mass. And we're going to do 1 over m times the double integral of x times the rho function and y times the rho function. And remember that m is given to be this formula here. So the first thing you want to do is find your m first, and then use that as a constant in the two formulas above when you're finding the x and y coordinates of the center of mass. So what you're finding is you're finding that point where the center of mass happens, where it's as if the entire mass is concentrated at that point. So let's look at an example of this. So this problem says find the mass and the center of mass of a triangular lamina with the vertices 0, 0, 1, 0, 1, 2 if the density function is rho is equal to 1 plus 3x plus y. So let's start off with our lamina. The vertices are 0, 0, 1, 0, and 0, 2. So what we have here is we have a triangular shape. And the equation of this line that connects them would be y equals 2x. 2 minus 2x, negative 2x plus 2. However you want to write that. Let's say 2 minus 2x here. We probably should back up and talk about how this happens, but here we have the point 1, 0, here we have the point 2, 0. So we have a slope of negative 2 over 1, and the y-intercept is 2. So y equals negative 2x plus 2, or 2 minus 2x. Now, when we do this, we're going to write our double integral. Our mass is going to be equal to the double integral over the region of rho of xy with respect to the area. So let's set up our double integral here. This is our mass, keep in mind. Our rho is 1 plus 3x plus y. And we need to think about this figure. This figure, I'm going to go from 0 to 2 minus 2x with respect to y. And then with respect to x, I'm going to go from 0 to 1. So then we're going to compute the mass. We're going to integrate from 0 to 1. And when we integrate with respect to y, we get y plus 3xy plus 1/2 y squared. And these bounds are from 0 to 2 minus 2x. And then we're going to integrate with respect to x afterwards. Now I'm bringing down my m equals because this is not the end of the problem. This will give us our mass, but our center of mass needs the mass in it. So we're going to start with this. Now when we plug in 2 minus 2x, we get 2 minus 2x plus 3x times 2 minus 2x plus 1/2 times 2 minus 2x quantity squared. And then when you plug in 0, we get minus 0. And then we're going to say dx out here. I'm going to move it over a little bit. So m equals, they didn't make it easy on us, did they? All this mess. 0 to 1. So we have 2 minus 2x plus 6x minus 6x squared plus 1/2. I can't do that in my head. I will do it wrong. So I'm going to waste another step here. So we have 4 minus 4x. Let's minus 8x. Let's do that again. 4 minus 2 times 2 is 4. And then we have minus 4x. Minus 4x is minus 8x plus 4x squared. And we're going to leave off the minus 0. We have to distribute that 1/2. So m equals the integral from 0 to 1. And we have 2 minus 2x plus 6x minus 6x squared plus 2 minus 4x plus 2x squared with respect to x. So we have minus 6x squared plus 2x squared is minus 4x squared. I'm going to start with that one. And we have minus 2x plus 6x minus 4x. Those cancel, and 2 plus 2 is 4. And now we can integrate with respect to x. We could pull that 4 out, but there's no need. So I'm just going to go ahead and integrate. So when we integrate, I'm going to keep my m equals to remind me I'm doing math. When we integrate, we get negative 4/3 x to the third plus 4x from 0 to 1. So we get negative 4/3 x to the third plus 4 minus 0 minus 0. So we have negative 4/3 plus 12/3 gives us 8/3 is our mass. So let's pause there, and our mass is 8/3, and then we're going to write down our center of mass formulas. Now I'm going to start just with the x formula. So I'm going to say the x coordinate, x bar. X bar has a different notation in statistics, so be careful. But here we're going to use it to stand for the center of mass. So the x coordinate for the center of mass is 1 over m times the double integral of x times rho of xy with respect to a. Now our x coordinate is going to be 1 over 8/3, so let's just go ahead and call it 3/8. We're going to have a double integral x, and our rho is 1 plus 3x plus y. I wrote it off to the side so I wouldn't have to scroll on the screen the whole time. And we're still going to have the bounds. I'm going to keep everything the same, 0 to 1 and 2 minus 2x with respect to y, and then with respect to x. So let's go ahead and keep our 3/8 out here, the integral from 0 to 1, and the integral from 0 to 2 minus 2x. We need to distribute the x plus 3x squared plus xy with respect to y, and then with respect to x, the integrals. So we have 3/8, the integral from 0 to 1. Remember that we're integrating with respect to y, so we're going to say xy plus 3x squared y plus 1/2 xy squared, and this will be from 0 to 2 minus 2x, and then we will integrate with respect to x. So let's bring down our 3/8 from 0 to 1. So when we plug in the y values, we get x times, I'm going to put a bracket here, 2 minus 2x for y, plus 3x squared times 2 minus 2x for y, plus 1/2 x. And I'm going to make a note over here, and I'm going to say 2 minus 2x quantity squared. I'm going to go ahead and plug it in to be 4, and then minus 4 is minus 8x, plus 4x squared. And then we're going to integrate with respect to x. So we're going to have 3/8, the integral from 0 to 1. And let's distribute. So we get 2x minus 2x squared plus 6x squared minus 6x to the third plus 1/2 of 4 is 2x minus 1/2 of 8 is 4x plus 1/2 of 4 is 2x to the third. Oh, there should be a squared here, dx. So this gives us 3/8. You could integrate that like it is, but I think you're out of your mind. Let's combine like terms. So we have negative 6x to the third, negative 6x to the third plus 2x to the third makes negative 4x to the third. Now we have negative 2x squared plus 6x squared minus 4x squared. That gives me 0 for that, and 2x plus 2x makes plus 4x. Respect to x afterwards. So we could factor out that 4 and cancel. I'm not going to. I'm just going to integrate. That's going to work out nicely. So we, the 4 cancels. This becomes x to the 4th plus 2x squared from 0 to 1. So we get 3/8 times negative 1 plus 2 gives me 1 times 3/8 is 3/8. So this is our x value of our center of mass. So now let's find the y value. So y bar is equal to the double 1 over m times the double integral over the region. And inside of the double integral, we have y times rho of xy with respect to the area. Now we're going to set this up the same as we did the last two. We're going to say 1 over the mass, which is 1 over 8/3, which we're going to go ahead and call 3/8 because 1 over a fraction means you flip it. We have the double integral, the integral from 0 to 1, the integral from from 0 to 2 minus 2x. And we're going to say y times our rho, which is 1 plus 3x plus y with respect to y, then with respect to x. So we have 3/8, 0 to 1, 0 to 2 minus 2x. When we distribute, we get y plus 3xy plus y squared, and we're going to integrate with respect to y and then with respect to x. So we have 3/8, the integral from 0 to 1. When we integrate y, we get 1/2 y squared. When we integrate the next one with y, we get 3/2 xy squared plus 1/3 y to the third from 0 to 2 minus 2x with respect to x. So we have 3/8, the integral from 0 to 1. So 1/2. Now remember, let's make this a bracket. Now remember that we have 2 minus 2x quantity squared. So this is equal to 4 minus 2 times 2 is 4, doubled is 8x plus 4x squared. So we have 1/2 parentheses, 4 minus 8x plus 4x squared plus 3/2 x times 4 minus 8x plus 4x squared plus 1/3. Now I'm going to go ahead and do it down here. I would normally do this at the top of my page, but I can't scroll up, so we're going to take 2 minus 2x times 4 minus 8x plus 4x squared. So when I multiply by 2, I get 8 minus 16x plus 8x squared minus 8x plus 16x squared minus 8x to the third. So when I combine these like terms, I'm going to start with the constant. I have 8. My x's, we have minus 24x. X squared says plus 24x squared minus 8x to the third. So I'm going to plug that in here. 8 minus 24x. I'm going to run out of space. Minus or plus 24x squared minus 8x to the third with respect to x is our next integral. So we have 3 over 8. The integral from 0 to 1. When we distribute this 1/2, we get 2 minus 4x plus 2x squared. Now we're going to multiply by 3/2 x. So 2 times 3 is 6x minus 4 times 3 is 12x squared plus 2 times 3 is 6x to the third plus 8 over 3. It's going to be terrible. Minus 8x plus 8x squared minus 8 over 3 x to the third. So now let's combine like terms. We have 2 and 8/3. So that's 14/3. Now we have minus 4x plus 6x minus 8x. That gives us minus 6x. 4 plus 6, negative 4 plus 6 is 2. Minus 8 is negative 6. And then we have 2x squared minus 12x squared is negative 10. Plus 8x squared makes a minus 2x squared. And then we have 6x to the third minus 8/3 x to the third is 18 minus 8 is 10/3 x to the third. So we have plus 10/3 x to the third, and we're going to integrate with respect to x. So now we can integrate this with respect to x, and we have 3/8. And when we integrate, we get 14/3 x minus 6 divided by 2 is 3x squared minus 2/3 x to the third plus 10 over 3 times 1/4, which would make 10 over 12, which is 5 over 6 x to the fourth. And we're integrating from 0 to 1. So let's plug those values in. So we have 3/8 times 14 over 3 minus 3 minus 2/3 plus 5 over 6 minus 0. I'm not going to do all those common denominators in my head, so let's find them. Common denominator is 6. So this will be 28, and this will be 18. And then we have 2 times 2 is 4, plus 5 over 6. So we have 3 over 8 times 28 minus 18 is 10. Minus 4 is 6, plus 5 is 11. So we get 11 over 16 to be our y value. So our center of mass, so let's summarize our answers down here. So for the mass, we had 8 over 3. And then for the x-coordinate, we had 3 over 8. And the y-coordinate, we had 11 over 16. So this is the point for the center of mass of the problem given. It's a little tedious, but you can do it. It's not overly hard. It just, this one was tedious, and I understand all that. I think that'll get you through the majority of the homework. Before we move on to inertia, though, let's look at one more problem. This problem comes straight out of WebAssign. It says a figure shows the lamina shaded according to the density function. The darker shading indicates higher density. Estimate the location of the center of mass of the lamina, then calculate its exact location. So I would estimate the center to be somewhere in this area. I think that there's no change in the y. If you look at the y's are exactly the same, so we're going to say halfway. So somewhere probably about in here would be my guess. So something comma 0.5, but then we're supposed to calculate it exactly, and this is our row. So let's set this up and say the center of mass. So let's start with m equals. I'm going to write in this space first of all. So the mass is equal to the double integral of rho, which is x to the third. And let's do dy and then dx, because I'm kind of in that mode today. Since this is a box, our bounds are both 0 to 1. So we have 0 to 1 on the y and 0 to 1 on the x. It doesn't matter which way we go on that. So this one shouldn't be as difficult as the last one we did. So let's integrate 0 to 1. And when we integrate with respect to y, we get x to the third y from 0 to 1. And then with respect to x, and I'm going to keep my mass to remind me. So when we plug these in, we get 1 to the third, so we get x to the third minus 0 with respect to x. So now we just have the integral from 0 to 1 of x to the third with respect to x. So when we integrate x to the third, we get 1/4 x to the fourth from 0 to 1. So when we plug in 1, we get 1/4 minus 0, which is 1/4. So our mass is 1/4. And remember, that's important when we're calculating our x bar and our y bar, the values for the center of mass. So x bar is equal to 1 over the mass times the double integral of the region of x times rho of xy with respect to x, with respect to a. So 1 over the mass, which is going to be 1 over 1/4, the double integral from 0 to 1, 0 to 1, x times x to the third, dy dx. Well, 1 over 1/4 is 4. The integral from 0 to 1, the integral from 0 to 1, x to the fourth, dy dx. You could probably skip that x to the fourth, but you should always do math at the level that any of your classmates could read. And if it was any more complicated, you should show it. So we have, when we integrate x to the fourth with respect to y, we get x to the fourth y from 0 to 1, which is just x to the fourth with respect to x, the integral. So now we have 4 times 1/5 x to the fourth, x to the fifth. Let me do that correctly. X to the fifth from 0 to 1. So when we plug in 1, we get 4 times 1/5 minus 0. So just 4 times 1/5, which is 4/5 for our x value, for the coordinate for the center of mass. So now let's go ahead and do y. I think it'll fit beside it. This one isn't as difficult as the last one. So 1 over the mass, the double integral of the region, y times rho of xy with respect to the area. So we get 1 over 1/4. I would tend to just write a 4 there. 0 to 1, y times x to the third. And then we're going to integrate with respect to y and then with respect to x. So we get 4 times the double integral from 0 to 1. We don't have to write that second integral. Let's go ahead and integrate it. So when we integrate y, we get 1/2 y squared times x to the third from 0 to 1. And then we'll still integrate with respect to x. So we have 4, and then the integral from 0 to 1. When we plug in 1, we get 1/2. So we have 1/2 x to the third from 0 to 1 with respect to x, because when you put in 0, it is 0. So we have 4 times, when we integrate, we get 1 over 2 times 4, which is 8 x to the fourth from 0 to 1. So that gives us 1/8 minus 0, which is 1/8. So we get 4 times 1/8, which is 1/2. So when we do this problem, our mass is 1/4, and our center of mass is at the point 4 over 5, 1/2. We estimated that to be 1/2, so that's pretty good. And 4 over 5 is about where we drew it to be, about where we thought it may be. So that's not too bad. All right, the last part of this section is inertia. So let's move into that. The moment of inertia. The moment of inertia is also called the second moment, and it's the moment of a particle of mass m about an axis. It's defined to be mr squared, where r is the distance from the particle to the axis. So that's important. We're going to move this into the concept of the lamina with a density function. So here we have the moment of inertia about the x-axis, and it's figured using the double integral with y squared times rho. And the moment of inertia about the y-axis is the double integral of x squared times rho. Thinking about the fact that we're talking about the distance from the particle to the axis, so that's why this is going on in this way. There's another formula. This is the moment of inertia about the origin, also called the polar moment of inertia. And if you look at the problem, it's got both of them, because if you were to split this and say the double integral of x squared rho xy dA plus the double integral of y squared rho of xy dA, when you add them, when you add those answers, you get the same answer. So our moment of inertia about the origin, or the polar moment, is equal to the moments about the x-axis and the y-axis added together. That may come in handy for you. Sometimes it'll come in super handy. So let's look at one of these problems. And I know that in your homework you're asked to find the moment of inertia about the x-axis, about the y-axis, and about the origin. So when you find the x and the y, you can add them to get the origin if you remember that that's allowed. So let's look at one of these problems. All right, so in this one we get to find the moments of inertia. We're given a region D and a density function rho. So remember your moments of inertia from the screen before. So let's start with I sub x. So I sub x is equal to the double integral, and you're going about the x-axis, so it's the double integral y squared times rho of xy with respect to a over the area of the region. So we're going to say the double integral, and y squared is y squared, and rho is ky squared. And let's go with respect to y and then with respect to x. So the outside one is x 1 to 3 for the bounds, and the inside integral is 1 to 4 for the bounds for y. So let's go ahead and multiply those y's. We have the double integral here, and so we have ky to the fourth. K is some constant, so we have dy dx. Now when we integrate with respect to y, we get 1/5 y to the fifth times k. Let's throw the k in the middle. 1/5 ky to the fifth from 1 to 4, and then we're going to integrate with respect to x. So we have the integral from 1 to 3, 4 to the fifth. So we have 1/5, and 4 to the fifth is 1024 over 5k. And we subtract 1, so we have 1 over 5k with respect to x. So let's combine these like terms. We have the integral from 1 to 3. 1024 minus 1 is 1023 over 5k. And now we're going to integrate with respect to x. So when we integrate with respect to x, we get 1023 over 5kx from 1 to 3. So let's evaluate. And we have 1023k, 1023 over 5 times k, parentheses 3 minus 1. So that's 2. So we get 2046 over 5 times k. That's our I sub x. That's our moment of inertia about the x-axis. So now let's go back and do our moment of inertia about the y-axis. So I sub y is equal to the double integral. And we have x squared times rho of xy with respect to the area. So we're going to say the double integral, x is 1 to 3, y is 1 to 4. We're going to say x squared times ky squared, and then we have with respect to y, and then with respect to x. I'm doing dy before dx today. Does it really matter? No. We learned last time how to switch them, so that's up to you. Remember that we're integrating here with respect to y, so we have x squared k times 1/3 y to the third from 1 to 4, and then we'll integrate with respect to x. So we have the integral from 1 to 3, x squared k times 1/3, and then 4 to the third is 64, minus 1 to the third is 1. So when we clean this up, we have 64 minus 1 is 63, divided by 3 is 21, x squared k, and then we're going to integrate with respect to x. So we're going to keep the 21k, and when we integrate x squared, we get 1/3 x to the third from 1 to 3, and so we have 21k times 1/3. Let's make that 7k. So we have 7k times x to the third. So 3 to the third is 27, minus 1 to the third is 1. So we have 7k times 26, which is 184k, and that's our I sub y. So that's two of them. And then when we find our moment of inertia about the origin, that means we add those two. So we have 2046 over 5k plus 184k. I am going to do common denominators because it works in my life. So 5 times 4 is 20, 2, 4, 9. So when we add these together, we get 2966 over 5k. So that is our moment of inertia about the origin. And that wraps up this lesson. I hope that it makes sense, and I hope that you have a great day. Thanks.